Hello, I'm going to be going over the naive Bayes model and machine learning, and let's go ahead and get started. All right, so the questions that I'm going to be answering in this video. So the general question I'm going to be answering is, what is a naive Bayes model? And to do this, I'm going to be answering 4 major questions, and then I'm going to break those up into sub-questions. So the first major question I'm going to answer is, what does a naive Bayes model do? And the way I'm going to answer this is I'm going to explain abstractly what a naive Bayes model does, or more generally what a naive Bayes model does. And then 1.2, I'm going to explain what a naive Bayes model does with a specific example. Now, the second major question I'm going to answer is, how does a naive Bayes model make classifications? And to answer that, I'm going to be answering 4 sub-questions. So 2.1, what is Bayes theorem? 2.2, how do we use Bayes theorem to compute the probability of an event given another event occurred? 2.3, how do we compute the terms in Bayes theorem from a data set? And 2.4, how does Bayes theorem help naive Bayes model make classifications? So I'm going to be answering those 2 major questions. Let's move on. So the questions to be answered continued. So the third major question is, I'm going to explain the naive Bayes model through a specific example, right? And I'm going to break this up into 3 sub-questions. So what is a specific scenario where we can use the naive Bayes model? 3.2, what is the data set for this specific scenario? 3.3, what is the class of a specific example using naive Bayes model? All right, so this is the third major question I'm going to answer. The fourth major question is, what happens when the feature is not present in the data set for a naive Bayes model? And I'll be answering this major question through these 3 sub-questions. So 4.1, what error occurs with the naive Bayes model when a feature is not present in the data set? 4.2, how do we fix the error from a feature not being in the data set? And 4.3, how does the error get fixed for a specific example using the naive Bayes model? So I'm going to be answering this major question with these 3 sub-questions. And this video, this is going to be split into 2 videos, and I'm going to be answering 1 and 2, those major questions in this video, and 3 and 4 in the next. And let's go ahead and continue. All right, so what does a naive Bayes model do? So a naive Bayes model is a machine learning model that puts examples, x of I, so x of I here it represents an example. So it puts examples into one class out of a set of classes, capital Y. Where capital Y, right, this is our set of classes, so we have class 1, class 2, class 3, and class M. So what a naive Bayes model does is it takes an example, x of I, and it assigns it one class out of these set of classes. Right? It does this by finding which class y of I, so y of I is a specific class, which class has the highest probability given the example x of I, or we're going to be computing the probability of class y of I given or conditioned under x of I. Right, and here I have a diagram demonstrating what the naive Bayes model does. So here it takes in a new example x of I, and x of I is essentially a bunch of features, so as feature 1, feature 2, feature 3, all the way to feature n. So we have a new example, x of I. This gets fed into the naive Bayes model. Naive Bayes model computes the probability of each class, so class 1, class 2, class all the way to class m, and it finds which class y of I has the largest probability out of this set. And in this case, it finds class 2 has the largest probability. And then the naive Bayes model returns that x of I will belong to class y2, or 2. Right, and this should be question 1.1 answer. What does the naive Bayes model do abstractly? All right, so let's move on. So here we're going to go over a specific example of what a naive Bayes model does. So here we have a specific example where we want to determine if a car is stolen or if a car is owned, right? These are our 2 classes. And we can measure the damage to the car, whether the car or not has a license plate, the miles driven by the car, and whether the car is registered with the state or not. All right, so our features here are damage And damage can be none, so there's no damage, mild, so there's mild damage, or high, so there's high damage to the car. License plate can be yes or no, so it can have a license plate or might not have a license plate. Miles driven can be low, so low number of miles driven, or mild, a mild number of miles driven, or high, a high number of miles driven on the car. And registered can be yes or no, so it is registered with the state or it isn't registered with the state. So these are the 4 features and all the values the features can take on for a specific example. Now the classes are class 1 is the car is stolen, and class 2 is owned, the car is owned. And so capital Y, our set of classes, is stolen or owned, right? So what we need to do is we need to take in a specific example, X of Y, which is how much damage, license plate, the miles driven, and whether it's registered or not. So we need to take in a specific car, measure these features, and determine whether it falls into the class stolen or it falls into the class owned, right? So let's say we find a new car, X of I, so X of I is here to represent our new car, and it has these features, right? So it has a mild amount of damage, it has a license plate, right? It has a mild number of miles driven, and it is registered with the state, right? So that's a new car, and these are the features that we measured for the car X of I. So now we compute the probability of each class given the X of I example, right? So here we compute the probability of Y equaling stolen, so the car being stolen, given X of I, the features, right? We find out that's equal to 0.3, so the 30% probability the car is stolen given the set of features that we have here, right? And then we compute the probability of Y equaling owned, so the probability of the class equaling owned, given the X of I features, and we find that 0.7, so there's a 70% chance that the car is owned given the features here, right? And we find that the probability of the car being owned or the class being owned is greater than the probability of the class being stolen or the car being stolen. So the car X of I, right, these set of features, is classified as owned. So our naive Bayes model will classify the new example X of I as owned. So Y of I will equal owned. Right, and this should be question 1.2 answered, a specific example of what a naive Bayes model does. So how does the naive Bayes model compute the probability? So remember, we computed the probability of Y of I condition with X of I on the previous slide, which is a conditional probability. This is the probability of event Y of I occurring given event X of I has occurred. And we need to compute this probability because our naive Bayes model uses this probability to determine which class X of I will belong to, right? And it does that by computing this probability for each class and picking which class has the maximum probability. So we need to be able to compute this. So let's do a simple example of computing this conditional probability. So a simple example of conditional probability is computing the probability of rolling a 6 with a die given that an even number has been rolled. Right? So rolling a 6 is our Y of I event, and X of I is rolling an even number. Right? So we want to compute the probability of rolling a 6 conditioned that we rolled an even number. Or said in terms of the random variables, the probability of Y of I equaling yes, conditioned that X of I is equal to yes. So before we are given the state of X of I, before we're given X of I is equal to yes, we could roll either a 1, a 2, a 3, a 4, a 5, or a 6. Right? And so we only have 1 out of 6 possibilities that end with Y of I equaling yes, so our probability of Y of I equaling yes is 1 out of 6. Right? That's our probability of rolling a 6 before we're given X of I. But after we're given that the random variable X of I is equal to yes, right, or we know that an even number has been rolled, this reduces the sample space to just 2, 4, and 6, since these are the only even numbers that we can roll. And now the probability of Y of I equaling yes, or the probability of us rolling a 6, condition that X of I is equal to yes, or that we roll the even number, now that's equal to 1/3, right? because we have one side that's a 6, and on the other two possible sides are just 2 and 4, so we have a 1 out of 3 chance of rolling a 6, given that x of I is equal to yes. And so this is an example of computing a conditional probability for a specific example, just looking at the sample space. So let's move on. Alright, now we're going to talk about Bayes' theorem. Bayes' theorem is a theorem in probability used to compute the conditional probability of an event given another event has occurred. Right, so here we have Bayes' theorem written out. It's the probability of y conditioned with x is equal to the probability of x conditioned with y times probability of y divided by the probability of x. And this is what we're going to use Bayes' theorem to compute the conditional probability that we need for our naive Bayes model. So let's do an example of that. So for example, in the case of y equaling rolling a 6, so that's our first event, and x equaling rolling an even number, that's our second event. Right? Let's compute the terms for Bayes' theorem. So the probability of x conditioned with y, or the probability of rolling an even number conditioned that we have rolled a 6, that's just equal to 1.0, because if we rolled a 6, then we'll automatically have rolled an even number. Alright, so that's the probability of x being even when y is 6. So the probability of y is equal to just 1/6, right? Because we only have one side that has a 6, and there's 5 other sides. So the probability of just y occurring, given no other information, is just 1 out of 6. Now the probability of x is the probability of rolling an even number, and since half the sides are even on a die, the probability of x occurring alone is just 1/2, or 0.5. Now that we computed the probability of x conditioned with y, the probability of y, and the probability of x, we can apply Bayes' theorem. We can apply Bayes' theorem to compute the probability of y conditioned with x, or the probability of rolling a 6, given that we've rolled an even number. And so that's going to equal the probability of x conditioned with y, which is 1.0, times the probability of y, which is 1/6, divided by the probability of x, which is 1/2, and this is 1/6 divided by 1/2, and that equals 1/3, which is the probability we computed on the previous slide. And so this is the probability of y occurring given x has occurred, the probability of us rolling a 6 given that we rolled a even number. And so this is an example of us applying Bayes' theorem to a particular example, and we should be able to apply this now to our naive Bayes model. And that should answer questions 2.1 and 2.2. Alright, let's move on. Alright, using Bayes' theorem in a naive Bayes model. So how do we compute the probability of x conditioned with y, or the probability of y, or the probability of x for our naive Bayes model when we have a specific scenario? Right, so take the scenario where we had to classify a car as either stolen or owned, and we were able to measure the damage, the license plate, the miles driven, and and whether the car is registered or not. Right, so how do we compute these three terms, the probability of x conditioned with y, or the probability of y, or the probability of x for a naive Bayes model given this particular scenario? Well, remember, for any machine learning model, we have a data set of examples, right? We have a data set of examples, and the frequency that a certain feature x, right, like damage equaling mild, or registered equaling yes, or class y, or like class y equaling owned, or class y equaling stolen. So the frequency that a certain feature x or class y occurs in the data set gives us our probability of x or y, right? So let me elaborate on that. So let's say we want to compute the probability of y equaling stolen, or the other class being stolen, right? So that's computing the probability of y here. So what we would do is we would take the total number of examples in the data set, which is 5, right? This is our data set. We have 5 examples. And we would take the total number of examples where the class is equal to stolen, and that's 1, 2, example 2, and example 4. So we have 2 where the examples class is equal to stolen. And we would, to compute the probability of y, we would take the ratio of the number of examples where that have a class equal to stolen divided by the total number of examples, right? That's equal to 2, right, divided by 5. And so the probability of y of I equaling stolen is just equal to 2 divided by 5, which is 0.4. And that's how we would compute these terms for our naive Bayes model given a data set for a particular scenario. All right, let's move on. So how do we compute all the terms for Bayes theorem in the data set? Right, so how do we compute the probability of x conditioned with y, the probability of x, and the probability of y? Right, how do we compute all of those? Well, what we're going to do is we're going to compute all of those we're going to compute all of those to compute the conditional probability of the probability of y of I equaling owned, condition that x of I is equal to miles driven is equal to mild, and all the other features are not measured yet. So this is the probability of y of I equaling owned, condition that x of I is equal to miles driven is equal to mild. Alright, so let's go ahead and compute these three terms for that conditional probability. So the probability of x, right, so the probability of the miles driven equaling mild is the number of examples with miles driven equal to mild, which is 1, 2, 3, right, that's 3, divided by the total number of examples, which is 5, so the probability of x, or the probability of miles driven equal to mild, is 3/5. Now the probability of y, right, is the probability of our class equaling owned, which is equal to the number of examples with our class equal to owned, which is 1, 2, 3, right, and divided by the total number of examples, which is 5. So the probability of our class equaling owned is going to be 3/5. And the probability of x conditioned with y, or the probability of observing miles driven is equal to mild, given that y is equal to owned, is equal to the number of examples with class equal to owned and miles driven equal to mild, and that's equal to 1 here, for example 1, and 1 here, for example 5. So that's 1, 2. So we have two examples with a number of where class is equal to owned and the miles driven is equal to mild, and this is divided by the number of examples with the class equal to owned, which is 3. And so this is 2 divided by 3, so the probability of x conditioned with y is 2/3. And so computing the probability of y conditioned with x, which is, remember, is the probability of y of I equaling owned, conditioned with x of I equal to miles driven equal to mild, that's going to be equal to the probability of x conditioned with y, which is 2/3, times the probability of y, which is 3/5, divided by the probability of x, which is 3/5, which is going to equal just 0.67, or 2/3. And so this is how we compute all three terms and apply Bayes theorem to compute the probability of y conditioned with x, so that our naive Bayes model can make a classification. All right, that should answer question 2.3, and let's move on. All right, so how does Bayes theorem allow us to make classifications? So if we're given a new example x of I, we use Bayes theorem and the data set to compute the probability of y conditioned with x for each class, right? So we would compute the probability of y equaling class 1 conditioned with x of I, the probability of y equaling class 2 conditioned with x of I, all the way to the probability of y equaling class m conditioned with x of I. And then we would choose the class with the highest probability of y conditioned with x of I, and that's going to be the class that our example x of I is going to be classified as. Right, so for the example where x of I is equal to miles driven is equal to mild, and all the other ones are undetermined, we can use the data set below and this example to classify this example using Bayes theorem and our naive Bayes model. So first what we're going to do is we're going to compute the probability of y equaling owned, or class 1, condition with x of I, which is going to equal 0.67. So this is the probability of y equaling owned, is 0.67. Now then we compute the probability of y equaling stolen, condition with x of I, right? And if you compute this using Bayes theorem, you find it's 0.33. And so now we have the conditional probabilities for each class given x of I. And since the probability of y of I equaling owned conditional if x of I is greater than the probability of y equaling stolen, the x of I is going to be classified as the owned class, or the car that x of I represents is going to be classified as being owned by a person. Alright, so that should tell you how, that should give you a specific example of how we use Bayes theorem and the naive Bayes model to make a classification of an example given a data set. Alright, so this is the end of the video over the naive Bayes model, and hopefully I've answered these two general questions. What does the naive Bayes model do? How does a naive Bayes model make naive Bayes model make classifications? If you think I haven't answered those, leave a comment down below about how I didn't, and I'll see you